inaccuracy of BJT current mirrors. So this is NAE, and therefore I will get I copy, and the goal is to make sure that goal is to make sure IREF is equal to I copy, but in reality I copy will roughly be equal to IREF unless you take some special precautions to make sure that they are exactly equal. So this is approximately equal. Okay. Now let us find out the reason why this is approximately equal. So what is the, so one inaccuracy is due to early voltage. Early voltage. And yesterday I gave you an example when this current source is used as a load in an amplifier. So when this is used as a load, so there will be swing over here. Okay, well, as soon as there is a swing happening over here, that means the VCE is going to change. So what is the current given by this one? It is IS e to the power of VBE by VT 1 plus VCE by VA. Okay, VI is the early voltage, right? So the bottom line is this I copy, I copy equal to N times IREF in this case. Okay, because I have put in NAE. Now this is possible. So I copy will exactly be equal to N IREF only when, so let's call this as Q1 and this as Q2, when area of Q2, sorry, when VCE of Q2, when VCE of Q2 is exactly equal to VCE of Q1. Okay, so only at one voltage at this point will this be perfectly matching, otherwise it won't be matching at all. Okay, now what is VCE of Q1? VCE of Q1 equal to VBE. So no way is this going to this. Ideally, I want lower compliance voltage. I want this voltage to be as low as possible. So I want this voltage to be equal to VCE SAT. So certainly these two currents, therefore there won't be 100% accuracy in copying. Okay, therefore I copy will be more than N IREF if VCE Q2 is greater than VBE and less than NIREF if VCE Q2 is less than VBE. Am I clear with this thing? So it won't be exactly equal. It will only be equal at one particular voltage. So therefore, the early voltage causes the inaccuracy in the current. Now,
Sir,
what else? Yes.
sir, A is the area.
Area, emitter area. AE stands for the emitter area. So I'm
Okay.
scaling the emitter areas. Now, how do you scale the emitter areas? You put multiples of this transistor, n of these in parallel. Yesterday I told you. How do you scale currents? By putting same transistors in parallel. Do not try to increase the area by layout. That is not a good practice. Okay, so if you want to increase, you use replicas of each replica. So by duplicating Q1 multiple times to realize Q2 is called replicating the same circuit, or is called replica biasing. So this is not really replica biasing that will be introduced in an advanced course. This is a very common technique used in IC design. Okay, in IC design, not in discrete component design that much. We don't do that. Okay. Mute your microphone. Okay. So now, what is the second source of? Can you think of what would be the second source of error here? Okay, what would be the second source of error? So area of this is this thing, emitter area. This will be n times AE. So whenever I write n times AE, that means I'm using n copies of Q1 to realize Q2. Okay, that is, so n times AE realized by duplicating or replicating, or in other words, not duplicating, duplicate is twice, replicating Q1 n times. Okay, that is how it is. Now, what do you think would be the cause of, what could be the cause, another cause for inaccuracy? The base current. Okay, so what is the base current here? Base current is going to be I copy by beta. And what is the base current here? It is going to be I copy by n beta, because the area is 1/n. Okay, now there will be an IC here, IC1, let's call it as IC1. Now VB of this and VB of this are the same. Let's assume that VCE is also the same. Okay, so assuming VCE of Q1 and Q2 are same. Okay, so what we can say is that IC1 equal to I copy by n, right? There is no question on this. We are not considering a mismatch due to the early voltage effect. Okay, so by writing KCL, therefore by KCL, CL at node X, at X, what do you get? We get I ref equal to IC1 plus I copy by beta plus I copy by n beta. Okay, therefore I copy equal to n by 1 plus n plus 1 beta I ref. Okay, does it make sense? Everyone okay with this? Any questions? Okay. Now, how do you, so you see that there is a huge error. So let's take some numbers. Okay. Let beta be equal to 200, n be equal to 40. Okay. And Iref be equal to 1 milliamp. Okay. So what is I copy? Can you tell me what is I copy? One of you please solve it and tell me. What is I copy? Please solve. How much?
39.195 million.
How much?
33.19.
33.195.
Are you sure? Is it that bad? Is it that bad? Okay, I did not calculate it. So I cannot believe that it is that bad. So I took beta of 200. So 41 divided by 200, right? 41 divided by 200 plus 1, 1.205. So 40 divided by 1.205. Wow, wow. You see that? Okay, I cooked up a number which gave you this kind of a messed up thing. Okay, so you see, you wanted how much? You wanted 40 milliamps. Are you getting 40 milliamps? No. Now let me tell you why is this a big problem? Why is this a big problem? So let's say I'm building a LED driver, okay, for the display, and I have 40 rows of displays. Okay, I have an LED here, LED diode that I need to turn on, and there are 40 such diodes. Okay, diode 1 to diode 40, which is the 40th column of the thing, and there will be 40 columns, and for every pixel there will be one diode, roughly. I mean, usually that there will be 3 diodes because RGB and all. Okay, so now these are all driven by current sources. Like this, they will be all driven by this current source. So I want exactly 1 milliamp to flow in each one of them. So that my intensity, I wanted it for a certain intensity, which is 1 milliamp is going to give me that much of intensity in the display and the brightness. And unfortunately, I'm getting almost 20% reduction in the intensity. Okay, or the red color, if this is the red pixel and the blue color pixel is something and the green color pixel is something, so red color needs 1 milliamp to this needs 1 milliamp, this needs 0.5 milliamps, and let's say this needs 0.25 milliamps. Now they are adding these colors are getting added in the ratio 1:2:2, 1:2:4. Okay, so now since they are getting added in this fashion, this combination would result in a certain color, correct? But what is happening is that my red color has become messed up because this is becoming, let's say, 0.8. So now I am, instead of seeing a whatever color, I don't know what is when it is R is 1 unit, okay, B is 0.5 unit, and G is 0.25 units. Okay, that time you might get a certain color. Let's say you get pink color. I don't know what color it is. Okay, but as soon as I change this from 1 unit to 0.8 units, this color will change from pink to something else. Okay, you have messed up your screen. So that's why you need to make sure that this technique won't work. Am I clear with this? Is that clear? Okay, so now let's see what we can do to overcome this. So if I have to now overcome this, I need to make sure that my this n plus 1 divided by beta term is as small as possible. This term I'm going to minimize and make it as small as possible. So what can we do to make sure that that is happening? So if I draw a circuit like this, IREF, so this is Q1, this is Q2. The area of this is AE and area of this is NAE. Okay, so this is going to be I copy by beta. This is going to be I copy by N beta. Okay, and this is node X, and this one is going to be IC1. Okay, and this is, let's call it as QB. Okay, this is going to be QF. Let's call it QF for now. Okay, so this is going to be IB comma F, and this is going to be IC comma F. Okay, this is the current. Now what is IC comma F? So IC comma F is actually the sum of the base currents. I copy divided by N beta. Therefore, IB comma F, if both QF and Q1, Q2 have the same beta, it is going to be I copy divided by beta square plus I copy divided by N beta square. And now apply KCL at this point. So KCL at a node X gives IREF. So I did not write IREF equal to IB comma F plus IC1, and therefore IREF equal to I copy by N plus, because this VBE and this VBE are the same, and assuming, let me say assuming VCEQ1, VCEQ2, I copy by N plus I copy by beta square plus I copy by N beta square. Okay, so then what do you get? So therefore I copy equal to N I ref divided by 1 plus 1 by beta square N plus 1. Okay, so now can you tell me what happens in the previous example case? So the denominator becomes, instead of 1.205, becomes 41 divided by, I said that beta is 200, right? 400,000 square plus 1.001025. 40 divided by 1.001025. So you get, in the previous example, you will get I copy equal to 39.959042 milliamps of current. Okay, so how much percentage error do you get? What is the percentage error? So percentage error equal to 40 minus 39.959042 divided by 40 times 100. So how much percentage is that? Can you tell me? Can you work that out?
Sir, 0.1025.
So this turns out to be 0.1025 percentage. Somebody wrote approximately 0.1. Now let me tell you how bad is this. This is really bad. You know, 0.1% is equal to, approximately equal to, a 10-bit system. Why? Because 10-bit has 1024 levels. 10-bit has 1024 levels. Now each level is how much then? Each level is how much? 1 divided by 1024 times 100%. Correct? Which is roughly equal to 0.1, right? Am I clear? Yes or no? Is that okay with everybody? So,
Sir,
yes.
so what do we mean by 10-bit system? I didn't understand.
If I have a system which is going to, if my pixels are going to be accurate up to 10 bit, what is the meaning of accurate up to 10 bit? Means if I have, the way this 10 bit system is defined is, I will define a full scale of the system, full scale of system. Now full scale means when there is full bright light. Okay, I want dark red color. That dark red is when R equal to 100, R equal to 255, or full scale, R equal to maximum. Red LED is glowing to the fullest extent, and red LED will glow to the maximum intensity when the current is, let's say, 100 milliamps. I'm just taking some numbers. These are ridiculous numbers. Okay, and green equal to 0 milliamp, and blue equal to 0 milliamp. That means my red light is going to the full scale for red light is 100 milliamps. Now, if I want, now I want to see really fine grains of red light, different shades of red light. So what will I do? If I use a 10-bit system, that means this 100 milliamps will be divided by 1024. Okay, so which will be roughly 0.1 milliamps. So when 0.1 milliamp of light is flowing through the LED, I'll see a faint light. 0.2, I see another a little brighter, like 0.3 milliamp, like that it will keep on going. But if I go for a 12-bit system, then my the faintness, the gradual increase in the intensity will be in finer steps of 100 milliamps. Full scale stays the same, divided by 4096. Okay, so it will increase in 0.025 milliamps or 25 microamp steps. The intensity will increase in finer steps. The finer steps the intensity increases, the quality of the image keep getting better and better. Sometimes HD image, why is HD so better? Ultra HD, why is that better? Because the quality of the image keeps on improving. Okay, so depending on the pixel, so the pixel size defines the quality of the pixel quality defines the. Now, now you can see that this one is giving, if I build a current mirror and I'm trying to mirror this current, my accuracy with which I'm mirroring is 0.1% error is there. This 0.1% error means I can maximum very well only see a 10-bit pixel, 10-bit image. Okay, but if I want really high good quality image, I need to digitize that image to 12-bit, 14-bit, 16-bit, whatever. Then I'll have to increase the resolution. That means this technique is not going to work. Okay, so you have to go for newer and newer techniques to do this. Now, if I want to further reduce this, what can I do? Can anybody suggest what can we do based on this topology? Anyone, any thoughts on how to further improve the accuracy? Can I get beta cube here? Can we get beta cube? Anyone? Ranveer saying?
We will do the same thing twice.
Same thing twice. So what will you do? So you are saying that, say, the amount of current that this part is stealing should be reduced. Correct?
Yes.
So that to reduce that, that means what we will do is I can now put in what will I do? I'll make this as the collector current. Yes, on the right, and connect this here. Yes or no? So now whatever current is flowing, this current is sum of these two. That current divided by beta is this current. Now that current divided by beta. So here this is already divided by beta. Here it gets divided, becomes beta square. Here it gets beta cube. And therefore the amount of current that we are stealing is reducing further. So we get a beta cube term. Am I clear? Okay. But is there a free lunch in the world? Is this free? Are we getting this for free, or is there a penalty that we are paying? What is the penalty? Anybody can suggest what is the penalty? Can you tell me? Now let us look at the penalty. In this topology, what was the VCE here? Equal to VBE. Okay. In this topology, what is the VCE of Q1? VBE plus another VBE, twice VBE. Am I correct? And if I add one more current source, it will become thrice VBE. Now, what do we say we want? If I want accurate mirroring, VCE of this one should be exactly equal to the VCE of this one. Yes, so the VCE of this one is increasing, but I want accurate mirroring, so I have to increase the VCE of this one as well, so that I can match the VCE of this and this. As soon as I start matching the VCE of this one, then the swing at this node will keep on dropping. So I pay the penalty in terms of the amount of swing. And the amount of swing decides what? The full scale of the system, which is 100 milliamps or whatever. These are some representatives. So I'm not the advanced course. I teach this how to build a system from a system spec. How do you build transistor level circuits and all? So am I clear? So there is a penalty here. Now keep in mind in the exam that you will be having, there will be these thoughtful questions. Okay. So it will have some design aspect, analysis aspect, and some tricky aspect. Okay. And some of these will be from my own bugs that I have seen in the industry. Very interesting bugs I've encountered. So I will outline some of those bugs and see how many of you can really solve it. I want to see your approach. Okay. Now, so basically, therefore, in a BJT current mirror, BJT based current mirror, current mirrors, okay. Inaccuracy is due to early voltage, due to early voltage. So to match VCEs, solution is match VCE. Okay. Due to base current, due to base current, stack transistors. As mentioned earlier. Okay, means stack transistors means this is what I call as this kind of stacking. So you are stacking in this direction. Okay, so here and this is coming in here. So VBE plus VBE like that it will keep on. So the penalty is pay the penalty of swing, pay swing penalty. Okay, now. So therefore, we have figured out how to match the current mirrors, the accuracy. Now we have to increase the output impedance. So how can we increase the output impedance? So you have studied already that output impedance increases if I start stacking transistors. This is another form of stacking. Okay, so Q1, Q2, Q3 and Q4. So what is the output impedance here? R out is roughly equal to GM4, RO4, RO2, right? Roughly equal to. Am I clear? Impedance looking down here. What is the compliance voltage here? Can anybody tell me what is the compliance voltage? V compliance voltage here. What is the voltage at this point? Twice VBE. What is the voltage here? Minus one more VBE. So what is this voltage here? VBE. Then what is the minimum voltage required across this? VCE sat. So compliance voltage equal to VBE plus VCE sat. Okay. So now how do you make sure, how do you design this topology such that V compliance is equal to twice VCE sat? That means this will be VCE sat, this will be VCE sat. How do you design this? And when you try to make this, how do you satisfy this as well as get 100% accuracy means you get match the VCE? That is a separate problem. So I won't be discussing this. I might give this as some homework problem. I'll give that as a homework problem and I want to see how many of you are creative in that. Okay, so this is what we are going to. So with this, I think I'll stop the BJT current mirrors. Now let's look at the MOSFET current mirrors. Okay, so now MOSFET current mirrors. So what will be the source of error? What will be the source of error in a MOSFET current mirror? So there is no base current, right? So what will be the source of error? The source of here it will be W by L, and if I want to multiply it n times, then I will put n of these in parallel, or I will call it n times W by L. Sorry, W by L. Keep in mind, never adjust the length of the transistor. Okay, so I copy. So scale currents by scaling W, not L. Very, very important. So here the inaccuracy in the current will come due to channel length modulation. Inaccuracy in mirroring is due to channel length modulation. Channel length modulation or unequal VDS. Okay, so that means I have to match the VDS of M1 and match the VDS of M2. Only when the two VDSs are matched will they cause the currents to be exactly equal. Okay, or scaled versions. Okay, here I copy is roughly equal to N times I ref. And the roughly equal to is because of the VDS. If they're not equal, then there will be a mismatch in the current. So key takeaway in MOSFET current mirrors is you scale the currents by scaling the width. Do not reduce the L. Do not. Okay, very, very important. Okay. Now, if I want to now increase the output impedance, I will do the same thing. I will cascode them. Okay, so I can cascode them. That increases the output impedance. So if this is M1 and this is M2, the R out is roughly equal to GM2 RO1 RO2, right? So you have already done this part. So this increases the output impedance. Okay, so now the final aspect which I have already discussed yesterday, is how do you realize current sources and current sinks? Okay, so BJT current source, I have this golden reference. Okay, somebody designed a nice, spent a lot of time, designed it and gave me this reference current. So I am realizing a current sink like this. I want to realize a current source, so which I have already discussed. So you make this diode connection and make this diode connection, and this is I copy source. Okay, or I copy SRC source, and if I want I sync, and this is I copy sync. Okay. So now if this area of this is AE, if this is AE and this is A, so let's call this as AEN, AEN, AEP, and this is N times AEP, and this is N times AEN, then I copy SRC is roughly equal to N times IREF, but there will be a lot of inaccuracies. There will be a base current here. Now this current is going in here, okay, and we'll have base current here, okay, base current here, and all those inaccuracies, I might give that as an analysis. I copy sync is roughly equal to N times IREF. Exact same thing can be done for a MOSFET. You replace this with a MOSFET. Okay, so let's call it Q1, Q2, so Q1, Q2, Q3, Q4, and Q5. Replace Q1, Q2, Q3, Q4, and Q5 with appropriately scaled W MOSFETs. Replace Q1 with appropriately scaled W MOSFETs to realize source current MOSFET current source and sink. Lengths alien. So else, no, I will write it here. Lengths of Q1, Q2, Q5 should be same, and lengths of Q3 and Q4 should be same. Means same. These are all NMOS and these are all PMOS. Okay. So if I replace Q1 with a MOSFET or the certain W by L and I want N times the current, then I will same current, then I'll keep this NMOS same W by L. Okay. And I will make this N times W by L. I cannot change the lengths of Q1, Q2 and Q5. Similarly, I can decide the W by L of this PMOS and then appropriately do NW by L of this one. I cannot change the lengths of these two. The lengths of these two should be identical, but the lengths of the NMOS and PMOS need not be the same. So lengths of NMOS and PMOS need not be the same. Okay. Okay, with this, I think I will wrap up the current mirrors. Okay, and tomorrow I will start the op-amp design. And then finally, I will, next week, I'll start feedback. Next week is, so I think I will spend roughly whole of next 3 weeks on feedback and frequency response for pre-compensation. I mean the phase margin and all stability. Okay. Any questions on current mirrors?